Alright, so now what we're going to talk about is finding the bases of a subspace. In particular, if I take a bunch of vectors and I just make a vector space out of them, what a basis for that subspace might be. So to sort of analogize what's happening here, let's say I'm in R3, and let's say I pick these three vectors and I say, okay, I'm going to take every possible way to combine these three vectors and see see whatever space that makes, and I end up with like this flat plane here, right? If I take these three vectors, but if I'm looking at these three vectors, like, do I need all three of these things to be a basis? No, right? Because this vector here is redundant. I can get rid of them, and I'm left with these two vectors, which works perfectly fine, right? As a basis, I get the same plane, and in fact, this is a basis because these two vectors are linearly independent. When I put this one in, it's not, right? And so we have a more complicated situation here where we have four vectors sit inside of R4, and so let's not even try to visualize that, and we're trying to see if they span. Well, maybe all of these vectors are linearly independent and we'll get all of R4, or maybe they're not. Maybe when I see how many are linearly independent of them, I might be able to get one of them from the other three, or two from the other two, or maybe they're all lying on the same line and I don't need all but one of them, right? I don't know that going in. And so what we're going to do is we're going to take these four vectors, we're going to find uh, uh, we're going to find out which one of these could form a basis, and then we're going to ask ourselves what the resultant dimension of the space is. So, if we want to find a basis for these four vector, or for the space spanned by these four vectors, what I'm really asking is, are there any linear dependencies between these vectors? And so, as usual, the way one addresses this is one takes the matrix form of these vectors. So let's write out the matrix form here. Minus 6, 4, minus 5, minus 4, minus 2, 3, 3. That's RREF them and see what results. And so we're going to take, oh, look at that, we're 4 by 4 already. Minus 4, minus 4, 1, minus 2, minus 3, minus 2, 3, minus 3, minus 7, minus 6, 4, minus 5, minus 4, minus 2, 3, 3. And if I do that, I get this reduced row echelon matrix, which is 1 followed by zeros in the first column, 0, 1, 0, 0, 1, 1, 0, 0. Okay, that's interesting. And 0, 0, 1, 0. And now that I've written out, let's see what this means. What does this mean? What is this telling us? Well, let's take a look at this column here. If I take a look at this column, we notice that there's a 1 and a 1 and a 1 and a 1 here, right? And so let's just temporarily pretend that this vector didn't exist. If this vector doesn't exist, this column doesn't exist, and this column doesn't exist. And so if this column doesn't exist, what I'm just looking at is, so ignoring that, I'll just rewrite it. I'm just looking at this matrix over here, right? That's the matrix you would have. And note that if I make that an augmented matrix, what you would observe is that this matrix has a valid solution, right? X1 being 1, x2 being 1. And if that's the case, what that's telling us is that this vector here is obtainable by these two vectors. In fact, you can obtain this vector by adding these two vectors together, and you can observe that minus 4 plus minus 3 is 7, minus 4 minus 2 is 6, 1, 3, 4, minus 2 minus 3 minus 5. And so if I'm trying to put together a basis for W, I don't need this vector, right? It's redundant. I already have this and that. I can put them together to make that what I need U for. So we know that since the third column is a linear combination of the first two, we may remove it. All right. So let's just ignore it then. What's left? What's left is this column. Now if I look at this compared to these first two, I can't combine these two, right, to be this last column. There's a, if I tried to, we would see from this row that there's no solution to such a vector equation. And since there's no solution to such a vector equation, these three vectors are in fact linearly independent. And so the resulting basis then is these three remaining vectors, right? So a basis of W is minus 4, 1, minus 2, minus 3, minus 2, 3, minus 3, and minus 4, minus 2, 3, 3. Those three vectors are all linearly independent of each other, and so they're not redundant. This x'd out vector was a linear combination of the first two, so it's redundant. All right, awesome. Now, the second question is, what's the dimension of this space? Well, it's built out of three linearly dependent vectors, so W has dimension 3. And there we go. All right. Thank you very much. I'll see you in the next video.